Hey everybody, how's it going? So last week we've completed the section of array, and then yesterday I have uploaded a video for the binary section, sum of two integers, which was a good one to practice bit manipulation. So I'm gonna continue with different sections from now on. So instead of focusing entirely one section in a week, I will probably try multiple different sections in a row so that I can catch up quickly. So today, what I'm going to cover is the three sections. And today, let's start with this first question, and then I can probably do the second in one session. So let's do it. So the goal of this two problem is to catch up technologies in DFS and BFS. So in an interview, in a real interview, after we finish solving in one technique, I can think of an interviewer is gonna probably suggest, can you do it in a different method with same runtime? So for example, if I have done this question in BFS and then interviewer is gonna ask DFS as an alternative solutions, so I will cover both methods in these sections so that we can be more resourceful. So that's the goal. And anyway, let's start with this first question. This is easy one, maximum depth of that binary tree. So we're given a root, which is a tree. So binary tree usually have left or right, or left and right, or nothing. And these bottom are called leaf, which has no child. And then the goal of this problem is to, so as usual, we're gonna start with goal setting, is to return the label. So I'm gonna return the max of label. And so that's the goal, which is integer. So constraints 1 over 1 to 3. So what should we care about in this situation? Definitely we should start with empty input. It is possible. So we should consider the edge case. Yes. So edge case. What about any other cases? Does the inside of number matter? Probably not in this situation. What we only care is the label, not the value itself of a node. So we're gonna ignore. So we can ignore the value, node value, because it doesn't matter in this case. What other constraints can we think of? So number of nodes is in the range of 10. Yeah, I think this is pretty much it. So as I mentioned, I want to cover idea 1 is to use BFS, and then idea 2, so interviewer is gonna ask use DFS instead. So don't try to focus one method because it is highly possible that we need to implement in both ways eventually. So, and both of these are open because as an upper bound, we only traverse each node at least once, or at most once. So theoretically, these idea 1 and idea 2 are, roughly has the same runtime. But as I mentioned, we should start with edge case. So if not root, we should return 0. And then let's declare answer starting with 1 actually. So now that we make sure we at least have a root, we can start with answer starting with 1. actually let's add one more constraint. So root level start with 1, not 0. So it's very good practice to clarify whether the root start with 0 as a level or not. Yeah. So anyway, let's use BFS first. So BFS start with declaring Q. So Q is first in, first out. I'm gonna run DQ, and then we should append the root and the level, which is 1 in this case. So Python use append to add some elements to the queue. Queue is the FIFO. So while queue exists, I'm gonna do the again. I'm gonna do three things. So to do 1, it's to get a node, and then to do 2 is the process answer. And then lastly, we're gonna next go to next, because this is iterative. So node and level can be popped from the queue, node from pop left. Python has pop left, meaning we're gonna pop the FIFO, the oldest one from the queue. So self answer should be updated. Self answer is the maximum of itself or the level. And then go to next. So what I mean next is that if 3 has left or right or both, we should call not the call, but we should put into queue so that we can go to next. So if node.left exists, we should append to queue, which is this node left itself, then the level +1. Why +1? Because we're going to next level. And similarly, if we have right, we should append right child and level +1 as usual. And then after loop is done, we just simply return answer. Okay. So this is theoretically open, even though the statistics seems a little slow. But yeah, in terms of theory, this is open, which is the optimal solution. So now what I've done in this queue, in this BFS, is to use the queue to track. So queue will track 3, and then after group 9, 20, 15, 7 is queued, and then it is popped in order. That's why I use pop left. So that's the BFS. Now what about DFS? So we can assume that interviewer is gonna ask, can you implement in DFS solution? So let's implement in DFS. So let's first declare DFS, which returns nothing, because we want to update the self answer. And then as a parameter, we're gonna take node node is a tree node, and then again we're gonna do three things. So 1, 2, and 3. So DFS always do the check validity first. I'm gonna explain later what it is, and then process answer, and then lastly we're gonna call recursively. So what I mean by the check validity is that if node doesn't exist, that means we are at the bottom. So we should just return and go back. Return. Yeah, and then we're gonna process the answer. Else, that means we are either 9 or 20 or 15 or 7. So we should definitely append. So actually, I forgot we should have level as an integer. Yeah, so self.answer is the maximum of self.answer or level. And then we're gonna call recursively. So I'm gonna do the same thing. If we have node left, we should call DFS again. So this time we're gonna call the child left, and then pass the level +1. Again, we are going to go deeper, so the level increments, and then node.right, do the same, and then so this is the function we have made. So lastly, in the main function of max depth, we're gonna call DFS, and then we should pass root. Then answer is starting from 1. So after DFS has finished, this self.answer should be updated from the second operation. So we're just gonna return self.answer. This is interesting. So let's debug what's going on. So we have started with 1. But then the answer is returning as 2, which is weird. So from the root, we have node, and then self.answer is not updated. So we should so we should run DFS. Of node left, which exists, and then label is 2, and 9 exists, so answer is updated as 2. Now 9 doesn't have any answer, that's why it's returning. I mean, it's the end. So we are stuck in the 9, but we want to return, right? Okay, so easy mistake is a beginner mistake, so we don't need return. So in the when we run DFS, if we do return of DFS, that means after 3 executed 9, after 9 is finished, then 3 returns, which are going to 20. But we want to execute DFS of right side, so we don't need return statement. Great, and then we submit. Nice, much faster runtime, 44 milliseconds, but theoretically this is open. So let's recap. After we have done edge case, we make sure root nodes start with 1, and then DFS, it's pretty much similar to BFS, but the difference is that we recursively call. So we should be careful, do not use return in this DFS of returning none, because we want, even if one side returned, we want to execute the right side. So instead of returning in the middle, we return at the end. Yeah, so that's the BFS and DFS in this easy question with max steps. Let's do the second one. Again, this is kind of like exercise for going forward, going more deeper questions. So these easy questions is really good practice to catch up BFS and DFS exercise. So the second question is the same tree. Let's see. So we are giving node root P and Q. We need to determine whether it is the same or not. That's why that function returns Boolean. Okay. So if P is Q, so return P is same as Q or not. But what's the constraint? So but we need to check every node, every children. So that's the main parts of this questions. We cannot simply return P equals Q because we need to check the values inside. So again, let's do maybe 1 or 2. As usual, do we have empty inputs? Yes, so the number of nodes is in range of 0, close bracket. So it is possible. So we need edge case. And then as a name constraint 2, is there anything we should concern about? Maybe not. Node value. So what did we check in the previous sections? We checked the root level start with 1. Root level. Actually, this question is interesting. That compared to the previous question, root level does not matter in this case, because what we care instead is the inside value. So let's do again. Idea 1 is to use BFS, and idea 2 is to use DFS. And similarly, they are both runtime is open. But anyway, let's start with the edge case. So if not P and not Q, we can return true. So that means both P and Q does not exist means equal, right? And if I'm gonna copy P exists but not Q, or P doesn't exist and Q, that means it's not same, so we're gonna return false. Okay, now we use the BFS. So again, we're gonna declare Q. This time we need P of Q of P and Q of Q. And DQ. So why do we separate? Because we want to check, we want to compare tree 1 and tree 2. So we need to have 2 Qs. Yeah, so then we're gonna start with append p to p, append node p, then append node q to the QQ. So while we have both P and Q, again we do the three things as usual. So get the nodes. So we get node P and node Q equals to node P of pop left, and then do the same for Q, pop left. Pop left takes fast in, fast out, and then what else? So we're gonna do the check comparison. So comparison means if P of value is different from Q of value, and then we return false. What else? What else can we do? A different section is different thing can be another thing we can do is that P, so P has node P has left and node Q doesn't have left child. That means we can return false. And same thing we can do is the right child. And yeah, I think that's pretty much for the checking. And then lastly, we going to append to the queue. So go to next cycle. So if we have node P left, that means this check is already done. So node Q left already also exists. Yeah, so we can just append. We can append two things. For P, for QP, we can append node P of the left. And then for node Q, we can append node Q of left. And then do the same for right side, right and right. Great. And then after this while loop is done, we can finally return true. Ooh, invalid syntax. Sorry, end operation. Okay, interesting. So for some reason, we are returning false. It's time for debug. So probably there are some typos. So let's see. So we have while. First we have 1 and 1. Value is the same. Both. Oh, actually. So this is silly mistake. So we should check Q left exists. Or we need to check P left doesn't exist, but Q left exists. And then we're gonna do the same for, okay, so P of right exists, but Q of right doesn't exist, or P of right doesn't exist, but Q of right exists, and then we're gonna return false. Yeah, so that's what we wanted. Another example is this symmetry. So what we can do is this null and 2, right? So this seems good. Another case is 1 to 1, and then 1 1 2. These are also symmetry. It looks good. And if the length is different, yes. So I'm gonna submit. Great. 40 milliseconds. So BFS also theoretically open. As you see, we have only traversed each node at most once. So this is working. This is BFS solution. Now, what about DFS? So this is the real last section, last part of this video is to use DFS for this question. So let's, as usual, let's create DFS. And then do we return anything? Yes, we're gonna return Boolean. And then what are we going to take is the node of P, which is tree node, and then node of Q, which is also tree node, and then do these three things again. 1, 2, 3. So I'm gonna check validity again, and then do the comparison, and then call recursively. So check validity means so we can simply copy and paste. We can actually move this edge case to here. Okay. And let's do the comparison. So comparison, we can do the same, copy and paste from the BFS solution. And then lastly, we're gonna call recursively. So we want to return BFS of child, which is left, and Q left, and we want to return DFS of right side, P and Q. So why do we use and instead of or? Because we want to check everything is exactly the same. So left side should be exactly the same, and right side also exactly should be the same. That's why we use and instead of or operation, and then we return the result. So even if left side is the same, but right side is different, and then using the and operation, we should return false. So that's the key part of this calling recursively part. And everything else should be the same as the BFS. So let's do the test. Okay. So what about 1, 2, 3, 1, 2, 3, 1, 2, 3, and 1, 2, 3. Oh, it's returning false. Wait, I'm not calling DFS yet. Sorry. So we should call DFS. So return DFS as an answer, and then P and Q. No types, don't have value. Ooh. Again, we should use node P and Q instead of P and Q. Sorry about that. Okay, so node P, we should replace. Sorry for the typo. Should be good. Okay, so we have 1, 2, 3, 1, 2, 3. What about symmetry? 1, 2, and 1 null and 2. Great. What about the different lengths? Okay, so I'm gonna submit. Okay, exactly same runtime 40 and 41. Pretty good. So, and memory usage is also top 5%. This is because we using DFS doesn't require any extra variable. So this is constant memory usage. So open runtime and of constant memory usage, which is pretty good. So what I have done is use BFS first and then try to implement in DFS. The difference between BFS is that BFS mainly traverse using queue, but BFS recursively call. And when we use the DFS, we need to be careful when we return whether it is the AND operation or OR operation. And both BFS and DFS usually use 3 to do 1, 2, 3. 1 is check the validity, 2 is the comparison or process some data, such as answer or level. And then finally, we're gonna call recursively or iteratively. So that's the BFS and DFS. It was pretty good exercise as a first step of the tree. So I'm gonna stop here. Thanks for watching. See you in the next video.